Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's Linode, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macy, and today I'm interviewing H.O. Maycotte about Molecula, a cloud-based feature store based on the open-source Pilosa project. So, H.O., can you start by introducing yourself?
Hello, everyone, and thanks for having me on here. My name's H.O. Maycotte. I'm originally from Mexico. I came to the United States to study electrical and computer engineering, and I've been sort of a crazy addicted entrepreneur ever since.
Do you remember how you first got involved in the area of data management?
Yeah, ever since I was a little kid, I was always obsessed with the idea that we as humans needed to evolve faster. And, it was pretty clear that data and AI were going to sort of be the path to get us there. The question for me was like, how do we beat Darwin? And so all of my companies have really been focused on trying to figure out how to consume and process and use more data along the way. I'm 8 companies in. So like I said, addicted entrepreneur. And I think we're starting to see some really interesting things happening out there today in terms of the super evolution that I dream of. You've probably watched the documentary Social Dilemma on Netflix, but data and AI is starting to do some really interesting things, that we can't totally explain at very large scale. We just have to figure out how to make that technology available to everyone. And so that has really been my life mission and why I focus on the problems that I do.
Can you give a bit of an overview about what it is that you're building now at Molecula and some of the story behind how you arrived at that particular problem and your particular approach to it?
Today, Molecula is positioned as an enterprise feature store. Like you said, we're built on the open source project Pilosa. Ultimately, our vision here is to help humans and machines make better decisions. It's kind of crazy to think about, but today the average company is only using about 1% of their data for analytics and machine learning. And it's not because we don't want to use more, but like physics is in the way for us being able to use more of that information. And we've been taught for decades to store it, but making it compute ready has been historically very difficult. And I lived this exact same story at our last company. We were a customer data platform for sports media and entertainment companies. And every time we signed a new customer, we'd sign hundreds of millions of fans with hundreds of millions of attributes. Think like social graphs, behavioral graphs from hundreds of different data sources. So think like preseason social and arena Wi-Fi. Our clients were like the NBA and Real Madrid and these huge, groups of fans that would come on every single time we signed these customers. And our system just could not keep up. We could not do real time on all of this data, and making it compute ready was incredibly difficult, right? We had huge clusters of Cassandra, of Elasticsearch, of Druid, and even our most important queries were starting to take longer and longer the more data we put into the system, and we were starting to have to face pre-processing and pre-aggregating and all the things that you do to sort of make data fast. No longer could we do the ad hoc queries that we wanted to do on those systems. And we had 2 engineers on our team that came up with this crazy idea, and they said, hey, H.O., we've been trading stocks using computers our entire career in these black box trading systems. In order to train models, we've always done this thing called feature extraction, which is the first process that you do when you do feature engineering. And at the time, I had no idea what they were saying, but I went with it. They further explained like, hey, if we could automatically extract features from data at the source, and we could store features instead of data in a purpose-built feature store, maybe we could solve some of these analytical problems. And I really had no other solutions at the time, and I told them, go for it. So they took 6 months. They came back with a feature store, and we put it up against some of these massive clusters of Elasticsearch servers. And we thought it was broken the first time we ran it because it was so fast, our trace was just not down sub-millisecond. And when we realized that, on 2 Pilosa servers, and Pilosa is what we call that original technology in the open source version, when we realized that these 2 Pilosa servers were doing the same query that, 40, 50 Elasticsearch servers were doing, in sub-millisecond versus, the 10, 15, 20 seconds that it was now taking Elasticsearch to do that same query, we realized that we had really sort of stumbled on something really unique. And we started pushing these bitmaps that we were using underneath the hood further and further. And so we taught it how to store integers and other data types. And we just, to our surprise, found that it could keep going as far as we pushed it. And so we ended up with 9 patents almost immediately. And it was about 4 years ago that that company was merged with another. And we went to our board and said, hey, we really think that we've got to teach the world how to operate on features and not data. Would you be okay if we spun these patents out? And that's what gave birth to the company that you're hearing about today, Molecula, and our efforts to go unlock data inside of these silos so that companies can put it to work.
As part of rolling out Molecula, or before then, as you mentioned, Pilosa is the open source sort of engine behind all of it. I'm wondering if you can give some of the story about what was your motivating factor for releasing that as open source, and just any of the additional effort that was needed to be able to decouple the Pilosa code from the company's internals to be able to release it as an open source project.
Yeah, great questions. I think one, our engineers had the foresight early on to completely decouple the code base. So we built Pilosa as a completely independent project from day one, not knowing that we were going to open source the technology ultimately. And then when we did spin that out about 4 years ago, it was clear that all we knew that Pilosa was good at is speed. And we knew that there had to be use cases, industries, verticals that could benefit from that speed, but we really didn't know what they were. So we knew that the right answer was to take that technology, put it out into the world to see what people would do with it. And sure enough, for about the first 3 years, we had, several thousand companies come through and use Pilosa and tell us, the types of use cases and workloads that they were interested in using Pilosa for. It allowed us to really extend Pilosa further so that we could support more use cases. We could, support dense, sparse, mixed density, ultra sparse data sets. We could support, integers and floating points. And so that time really gave us the ammo that we needed to really figure out our commercial strategy. And it was last year that we decided to start commercializing the technology under the brand Molecula. It's been really exciting to get to engage with the community. I will say, though, over the last year, we only had a finite amount of resources. It wasn't until late December that we raised a very large Series A. So I would say for about the last year, we've really shifted focus on figuring out how to commercialize the technology. So most of our efforts have been on the Molecula side. And it's going to be later this year that we've got some really, really exciting plans with open source, again, to reinvigorate the open source community and continue to reinvest heavily in that community as we commercialize and make the best of the Molecula side from all of our learnings. And, it's probably worth touching on the Pilosa side, the core systems are all written in Go. It's a distributed system. A lot of the cluster management is something that falls to the user who's operating these clusters. So a lot of what we've been doing on the Molecula side has been focused on ingest, on scaling and cluster management. We have some very, very, very large use cases. So making sure that the technology is stable and adoptable. And it's not just about getting data in, which is a lot of what we focused on, but it's about being able to get data out. So being able to bring traditional query interfaces like SQL so that it's just as easy to get data out. So Pilosa still requires quite a bit of effort to sort of set up your data models, to manage the clusters. On the Molecula side, a lot of that is taken care of, right? Adoptability was a huge focus for us on the Molecula side, and we're excited to push a lot of that innovation and code base and technology back down into Pilosa.
You mentioned that the Pilosa project itself is creating this bitmap index for being able to automatically extract features from the underlying source data, and that allows you to execute a lot faster on being able to perform these aggregate analyses on it. And I'm wondering if you can just give a bit of an overview about the types of problems and use cases that allows you to solve for, and some of the purpose-built solutions that you're providing through Molecula based on that.
Yeah, definitely. And I think it is super important to state how important that automatic extraction of features is. Like, we like to think of the data sitting in a Molecula cluster as compute ready. So having compute ready data to me is an incredibly important part of the puzzle. But once the data is in Molecula, the types of workloads that we're very, very, very good at are your typical analytical workloads. So any type of OLAP workload is something that we would knock out of the park, especially when you start to get into really complicated combinations of query types. So top ends with filters or top Ks, group bys, things that on their own might be difficult in a typical system. But I think maybe most importantly is to be able to do all of this without pre-joining or pre-aggregating data, right? Today, a lot of the data warehouses that exist, in fact, only 1 out of 7 copies of data is original. The other 6 are copies that are being made to pre-join and pre-process data and to get the decisions and insights from the original data. And so just the fact that you no longer have to pre-join data and you can do those joins at query time is really just a game changer in terms of your ability to have, again, compute-ready data.
One of the types of patterns that you'll see a lot in data warehouses is that you have these large dimensional tables that are, I imagine, some of the cases where you're extracting the features from the source data, but then you also will need to be able to join in much smaller data sets that have concrete facts about the information that you're trying to derive. And in the Molecula and Pilosa approach, where you're generating this bitmap from the source data, where you're reducing its dimensionality, how does that play out when you're also trying to join in some of those concrete facts about the source data? Is that something where you would leave the source data in situ and then Molecula would query against that at the analysis time? Or would you also reflect that source data into an accompanying system for being able to join it together?
So when the data comes into Molecula, we put it into what are called feature tables. And as you suggested, the entire process of feature extraction is really the dimensionality reduction of data. And dimensional data starts with star schemas and relational constructs and sometimes some very complex structures. And at the end of the day, the ultimate goal is to get it into a two-dimensional space, right? Like objects and attributes. Like the data model for our customers are usually pretty boring. It's like clients and all their attributes. But a lot of that data that you described, the smaller data sets, just gets dimensionally reduced into that two-dimensional space. Or it can also exist as a feature table alongside, the other data, and that join can happen at query time. And back to sort of the original problem, like everyone in the world today, sometimes scale out does not make a difference in terms of query speeds, right? You can add as many servers as you want and you find a latency floor. And so being able to shatter that latency floor means you can now do transformations, you can do those joins at the query. And so if you can't dimensionally reduce it into the same feature table, you can put it into an adjacent feature table and still reap the benefits of that sort of extreme query speed that you're getting out the other end.
And you mentioned that some of the progeny for this particular solution was a collection of Elasticsearch and Cassandra and various other storage technologies that you were trying to use because of their specific capabilities for doing different types of analyses or aggregates. I'm wondering, what are some of the other technologies or architectural patterns that you typically see some of your customers moving from once they start to adopt Molecula, and some of the ways that Molecula can replace some of these heavyweight workflows?
Definitely, we end up replacing large swaths of what I like to call information era technology. We don't typically go in with that as a value proposition when we're selling the technology. We try to focus more on the value that's getting unlocked. But certainly our clients very quickly catch on to the fact that a lot of this can be eliminated. So we see a lot of Druid, a lot of Mongo, a lot of Elastic being removed. And it's really all around, the ad hoc queries, the real-time queries, and the systems that are being used to sort of pre-join and pre-process the data. Those can all be eliminated when you can do all of those things in real time. And, we probably all seen these modern architectural drawings that Andreessen Horowitz has put out as their reference diagrams for the future, right? Like, what does a modern data stack look like? And what does a modern AI stack look like? And they all have component after component for ad hoc and for real time. And all of these things can go away with a feature store. So those are the very things that we're replacing once we get implemented with our clients.
RudderStack's smart customer data pipeline is warehouse first. It builds your customer data warehouse and your identity graph on your data warehouse with support for Snowflake, Google BigQuery, Amazon Redshift, and more. Their SDKs and plugins make event streaming easy, and their integrations with cloud applications like Salesforce and Zendesk help you go beyond event streaming. With RudderStack, you can use all of your customer data to answer more difficult questions and send those insights to your whole customer data stack. Sign up for free at dataengineeringpodcast.com/rudder today. You mentioned a few times feature extraction, and I know that you've also moved into the space of Molecula being offered as a feature store. Can you describe some of the nuance there about the difference between extracting features and a feature store and just some of the additional operations that are necessary to go from one to the other?
I'm excited as a founder and as an entrepreneur to be at the table while the definition of feature store is being established. I think it's a fairly new construct. And really over the last 6 months, we've seen it explode in terms of its popularity. We see platforms repositioning as feature stores or emerging as feature stores. We also end up with Fortune 100 clients all the time who have been building feature stores inside of their stacks for years to try to solve for this problem. What we find pretty much across the board is that they're all really reference architectures for common information era systems used to store features, right? So they are definitely extracting features, although most of the time that's a manual process. And what these modern feature stores are allowing you to do is to store those features and reuse them. But they're storing features in a data store, not in a feature store. So I'd say what is so radically different about our approach is that we see ourselves as the evolution to the data store, a feature-first file format that is designed specifically to store features. If you go back to the history of file formats, I assert that the very first file format was the file allocation tables used to store data on hard drives, although most would argue that it's really the transactional databases that were invented in the 70s with row-wise formats. And then we very quickly had the OLAP cubes and what eventually has become sort of the columnar systems emerge to solve the analytical problems. We see this feature-first format as the evolution and the next step from columnar, right? Columnar still scanning the entire column. This feature-first format that we built from the ground up, we wrote it in Go, literally reads and writes at the value, at the feature, without needing to scan rows, without needing to scan columns. And it's unimaginably fast because it's essentially deconstructed data into its most elemental form. These massive bitmaps that we shard and homomorphically compress, get loaded into memory. And when you think you're running a SQL query, you're really just pulling bitmaps out of memory and pushing them through the processor. And often in one clock cycle, you're doing what might have taken seconds, minutes, hours. We still see long running queries that take half days and days in our customers. Those now happen in milliseconds. And it's been really, really fascinating to see the evolution of that from when we first invented it to now. But long story short, we see even our competitor feature stores really needing a feature store underneath, not a data store that's storing features. A lot of the problems we're in today is because data stores don't scale to the type of workloads that we're going to need to make real-time decisions. So we really want to solve the feature store problem for even the feature stores. But certainly we believe that the entirety of the machine learning lifecycle should be operating on features, whether you're doing simple evolutions of analytics, right? You're going from descriptive and diagnostic to predictive and prescriptive and proactive, or, an AI infrastructure component, or one of these new fields in AI, around explainability and ethics and bias. We see all of that ultimately sitting on top of features in a real feature store, not on features being stored in a data store. So that is really the differentiator.
The way that I've come to understand features in the context of machine learning is sort of a derived fact based on underlying individual elements of data. So one of the examples that came up in a previous podcast is for maybe an Uber Eats customer, you have the information about the last order that they placed, the restaurant that it was, the timing of it, and from that, you have some of those historical context. And so you might derive a feature based on that about this particular user's preferred type of cuisine. And so in that context where the extracted or the derived feature is this piece of aggregate information, how does that compare to the feature extraction that you're doing with the bitmap index versus the feature that you're storing in the feature store for the machine learning context?
Really, at the end of the day, they're the same thing. And I think what we've pioneered is the coarse grain automated feature extraction directly from the source. So we typically attach ourselves to things like Kafka topics, change data capture feeds. And much like, a Fivetran, we don't make any decisions about what data gets put into the feature store or not. There is no quote unquote feature selection in our automated process. We just move your entire data model into the feature store. We look for schema changes, inserts, deletes, updates, and those automatically make it back into the feature store. If you need to further refine that data, combine it, do transformations on it, calculations on it, those are happening as a further layer of the feature store. And that's where you really start to see feature selection and a lot of what you're talking about. But we like to think that the data is already in a computable state, right? You don't have to go back to IT and ask them to do another major drop of a file into S3. Like, all of the data is there. And not only is it there, but it's getting updated within milliseconds of the change happening in the source systems. And a lot of times we see our customers have hundreds. We've never seen thousands of databases yet connected into a single feature store, but we have one customer that has 400 different databases inside of their enterprise that contain different aspects of their customers. So they've wired those up to feed the changes into the feature store. And now they have one place where all those 400 databases are consolidated into one view of that customer.
In that case, the auto-generated feature might be the frequency at which a particular user orders from a particular restaurant, and then the higher order feature would be the derivation of their preferred type of cuisine based on that, automatically extracted feature.
Exactly, or scoring or ranking. And again, a lot of that stuff we prefer you to do in a calculation and not have to pre-store, right? With information era systems, a lot of times, even once you do the manual feature extraction and get your feature sets the way you want them, you're then running a batch process to score and rank them. And then you're running your behavioral based personalization or whatever it is on batch scores, because this underlying feature store is so unbelievably fast, we can do that in the UX. So a lot of the use cases that we're powering are real-time personalization, real-time risk underwriting that are updated to the millisecond based on the totality of the data available to make that decision without the batch processes in the middle.
Digging a bit more into the Molecula platform itself, can you describe some of the overall architecture of the system and some of the ways that the design of that platform and its overall goals have changed or evolved since you first began working on it and building on top of the underlying Pilosa engine?
So there's really three major components to Molecula. One, and obviously most importantly, it's Pilosa, right? Pilosa is the feature-first file format that we invented 7 years ago. Then we have the Molecula platform wrapped around it. Molecula is really doing the orchestration of Pilosa and all of the services required to sort of deliver an end-to-end experience. And then we have these things called taps. Taps are what we use to get data into the platform. So a tap gets attached to a downstream database, Cassandra, MySQL, Mongo, S3, wherever the source data is, the tap is attached, and that tap is where the automated feature extraction is happening. Then we're only routing feature changes to the feature store. So we end up getting, I'd say, anywhere between 10 and 20x compression on the underlying data in terms of the features that are getting sent across the wire and then the features that are getting stored. That's one of the magical qualities of features. They're a fraction of the size of the data they're representing without any loss, without any impact to processing time to have to compress or decompress. It's pretty amazing. So it starts at the tap, it moves into the feature store, it gets stored in the file system that we've invented, and then on the other end, it's consumed using client libraries, it's consumed using SQL. We have a proprietary bitwise query language that we call PQL, although that is slowly getting retired. And so those are the various ways that you communicate directly with the feature store.
And I actually had one of your engineers on, I believe about a year ago, to talk about Pilosa. So for anybody who wants to get some more context, I'll add a link to the show notes. But I'm interested in digging a bit more into that evolution from the proprietary or specific query language for your bitmap index to the more generally available and more widely understood SQL language, and just some of the motivation for going that direction and some of the complexities that have arisen from trying to be able to map the concepts for this very specialized storage engine to the generalized declarative SQL language.
Yeah, no question. I think, obviously we are very familiar with Pilosa and our own technology, and we know how fast it can be in terms of these analytical workloads. But it has been quite a journey being able to explain it to and convince others that it can defy physics and defy gravity, right? We're so used to these information era systems that can't solve these problems. I mean, we regularly have rooms full of people doubting our ability to do these things in real time. They're sure that we pre-joined or pre-processed the data, and we haven't. But it's not historically easy to get data into Pilosa. It's not easy to get data out of Pilosa. And so adoptability was our major compass on the Molecula side, making it easy to use, adoptable, relatable, so that it was more familiar in terms of a traditional data system. And so we are going to invest very heavily on the open source side over the next year. So starting in Q2 of this year, we'll be putting a ton of that functionality back into the open source. And for lack of a better description, Pilosa and the open source are going to become the offline feature store, and Molecula is in the process of becoming the online feature store. And we've all learned a lot about licensing and open source, so we're still working through some of those details in terms of exactly how we're going to do that. But we are going to take some really big risks, and we think this is bigger than us as we did originally, and we really do want even our competitors collaborating on the source format that we think is going to power the future of machine learning. So yeah, we have a lot of work to do still.
Digging a bit more into the actual internal storage layout and the data model behind Pilosa, I'm wondering if you can just describe some of the specifics there and some of the ways that somebody who's unfamiliar with this technology and the concept of the bitmap indexes that you're creating and the availability for being able to run compute across these sparse matrices, and just how that might map into the way that they think about the data modeling aspects of it.
So today we're trying to eliminate the need to have to think about it. With Pilosa, you still have to, but that's going to go away shortly. At the end of the day, it really is mind-bogglingly simple. Like you were saying earlier, like the process of feature extraction, we've taken to the absolute most fundamental level. Like literally an integer is a yes or no question. Everything is a yes or no question, right? So you've got objects on one side and attributes across the top. And the attribute is literally, is HO44 yes or no? Is HO45 yes or no? Now, we don't create extra overhead if we don't have to. So there's some really fascinating tricks that you can teach bitmaps, right? Like roaring bitmaps, and our modification of roaring bitmaps has been a huge part of our ability to compress and operate on compressed bitmaps. Then sharding strategies and how you distribute this in a cluster is yet a whole nother set of considerations. We use tricks like bit slice indexing to be able to store 64-bit numbers in a much more compressed representation. And what's been just fascinating about these bitmaps is how far we've been able to push them to solve both workloads and data types that nobody had ever pushed them to do so. Bitmaps are not new, and a lot of databases use bitmaps for particular index types. We just flipped it and said, no, forget it. The bitmap is the database. And it's called features. So it really is unbelievably simple. And so with Molecula, you don't even need to think about that. You change your schema in your source system. It changes the schema down underneath. And you run queries on the other end as if you were querying the original system. So we've really made that transparent for the end user, because otherwise it really is a major leap in terms of conception, in terms of how to do that. So that's where a lot of our IP has been focused on over the last couple of years.
Digging further into this, so for somebody who's familiar with a more sort of what you've been calling an information age system, so in particular, I'm thinking about it for somebody who wants to be able to keep all their source data in their source systems, but still be able to query across it and join an aggregate. The canonical example of that right now is the Presto/Trino project, where you can have this SQL engine that connects up to all these various different data sources, and then you might run these queries to perform aggregates or analyses across these different systems, or use it to extract information from those systems to load it into a different data store, into object storage, and then be able to do downstream queries against that. How does that concept of querying against these different source systems and possibly migrating it into other systems for being able to do more refined analytics compare to the workflow for somebody who's using Molecula and building these feature extractions and derived features on top of those source data systems and running these aggregate queries across it?
I think it really depends on your use case, right? I like to say that we solve for the machine scale use cases. And I think a lot of those tools are really good at the human scale. If sub-millisecond latencies on the data, regardless of the complexity of the query, is not important, then sure, fan out your query, wait for the responses to come back, stitch them together, and then look at that response, right? That might be good for an analyst trying to get an answer out of a complex set of databases inside of a very large company, but you're never going to power a real-time decision off of that, right? You're never going to make a recommendation to a physician at the point of care about what the diagnosis may be based on all of the historical data about every patient that's come through that hospital room. So, and weirdly enough, one of the things that I've learned that's been very difficult to sort of accept is that real time is still a really ephemeral use case. What people define as real time today is still not. Sometimes real time can be minutes, sometimes it can be in the same day. But if you need to make a decision right at that moment based on all of the available data without having to go through batch and pre-processing and pre-computation, there really is no other way to do it. So again, if you're okay with the latency and you can wait minutes, hours, or days for the query to come back, then things like federation are perfect. If you don't care that your BI reports might be up to 2 weeks late, which we see very often, then batch is fine and aggregation is fine. And this is why things like IoT have been so very difficult. I can't talk specifically about names, but we're working with a very large car manufacturer right now that generates like 1 trillion events off their power plants and supply chains every day, right? This is all the IoT data that's getting created. Well, IoT data is worthless on its own, right? It's got a serial number, it's got a timestamp and a measurement. You can't make a decision on that. So all of these trillions of events have to get moved and piped back to a data center where they have to be pre-joined with the business data and the inventory data and the customer data. And then only then can they start to make calculations about how a missing part might impact that supply chain in a different region. And by the time that happens, you're talking about hours or days or sometimes even weeks later when that decision really needed to happen instantaneously. And so those are the types of use cases that we're very excited about: security, healthcare, IoT, where you really need real time.
Your mention of the IoT use case put me in mind of another interview I did in the past about the SWIM framework or SWIM OS, which is a different model for being able to compute across real-time streaming data rather than having it go all the way back to the data warehouse and then perform your analyses. You do it in flight so that you can get that real-time feedback rather than having to figure out like, okay, well, I've joined it across all this other information, just keeping it, stateful and resident in memory, and then having the different nodes within the overall network be able to cooperate for being able to build out these computations. And one of the examples that they provided was a manufacturing facility for aircraft being able to do real-time, up-to-the-date tracking of the various components of inventory because of the complex number of pieces that go into building an aircraft, where it had been a problem that was causing them, significant pain. And then they implemented this system of being able to compute it in real time. And it was just a complete revolution in terms of their ability to be able to keep up to date with the state of their business.
Absolutely. And I don't think we can even fathom what that revolution is going to look like when we really unlock real time. On the Molecula side, we're in the process of building out our cloud version right now. And, we're thinking about it as an underlay to all of the major clouds. It's completely hybrid, but it's a network of compute ready data where you tap the source wherever it happens to sit and you plug a model in and make a decision. And, it's that easy and that fast. You don't have to worry about all of the architecting and deploying and securing and monitoring that typically goes into preparing data for analysis. And so I don't exactly know what the world looks like when this problem is solved, but I do think it is the biggest problem in the world right now.
So the technology that we're discussing here, and as you've alluded to, it's something that can be difficult for people to be able to wrap their heads around because it's such a paradigm shift from the way that people are used to thinking about the problem. And so as you are building out the platform and educating your customers and educating potential customers about it or onboarding people, what are some of the most underutilized capabilities of the system or most misunderstood concepts or some of the biggest challenges in helping people to arrive at an understanding of what the capabilities are for this platform?
I think at the end of the day, because latency has been such a problem, we've created databases for everything, right? Like we have time series databases. We now have feature stores that are storing features in databases. The world does not need yet another like database type, but disabusing people of the notion that they have to go use a whole combination of databases to solve a single problem, I think is one of the most misunderstood things. Like once you shatter that latency floor, time, joins, transformations, those all just happen at the query, right? You shift the power to the data scientist and to the end user. I think it's also very important for us to say, and this is very appropriate for your series, is that we sell to data engineers, right? Our internal mission this year is to turn data engineers into heroes. We don't sell to data scientists. We don't sell to the end app builders and users. They're the beneficiaries. But you no longer have to go build a special database and data set for every single data type and then figure out how to stitch them all together. So once the data is loaded into the feature store, it's there to solve time series problems, and it's there to solve complex joins. It's there to solve analytical queries for feature reuse. You can do anything you could do with a conventional system with it, except it's just very, very fast.
Just digging a bit more into that aspect of things. So you mentioned that you have these different taps for being able to migrate information into the Molecula platform, and that there's the SQL interface for being able to query across it and perform these analyses and feature engineering on top of it. But can you just talk through some of the available interfaces and extension points for Molecula and Pilosa for being able to onboard new data sets, or some of the considerations that end users need to think about as far as making sure that the information in their source systems stays up to date in Molecula, and just the overall process of keeping everything in sync along those axes?
Yeah, I think if my implementation team were here, they'd probably kick me under the table, but we've really solved for a lot of that, right? So once you implement a tap, we pick up on those changes. I mean, no question, our absolute favorite way to ingest data is through a data pipeline like Kafka. You attach yourself to a topic, you watch the schema registry, and as changes happen and as updates happen in that topic, the feature store updates itself. Right. So really very little intervention on the end user's part to have to change anything in the actual feature store. And then on the query side, same thing, right? Once you've built out your queries, a lot of them are portable. I think maybe an area for innovation and investment in the future is building out APIs that mirror existing APIs, right? Like the Mongo API or the Cassandra API, so that you can bring already written queries for other platforms to the feature store. But otherwise, the benefits are so overwhelming that sometimes you do have to rewrite some queries or rethink the way that you consume the data. But often we're solving use cases that the information era systems couldn't solve. Like we have one customer that just brought us a use case, and they do 300 billion transactions a day. There was no information era system that solved that. So it's not like they had 10 years of queries that they have to go rewrite. So we are trying to make it as transparent and easy as possible. It is not always the case, but it's not a huge lift to get there.
Modern data teams are dealing with a lot of complexity in their data pipelines and analytical code. Monitoring data quality, tracing incidents, and testing changes can be daunting and often takes hours or days. Datafold helps data teams gain visibility and confidence in the quality of their analytical data through data profiling, column-level lineage, and intelligent anomaly detection. Datafold also helps automate regression testing of ETL code with its data diff feature that instantly shows how a change in ETL or BI code affects the produced data, both on a statistical level and down to individual rows and values. Datafold integrates with all major data warehouses, as well as frameworks such as Airflow and dbt, and seamlessly plugs into CI workflows. Go to dataengineeringpodcast.com/Datafold today to start a 30-day trial of Datafold. Once you sign up and create an alert in Datafold for your company data, they'll send you a cool water flask. One of the other things that you mentioned earlier is that with the fact that you have Pilosa out in the open, available for other people to use, and you're working on making it easier to adopt and easier to integrate, and you're hoping that other companies adopt it for different use cases, I'm curious what you see as some of the downstream potential for other types of systems to be built on top of this, or other ways that this technology can be used to benefit different companies or different data use cases.
I think at the end of the day, just true utility style instant access to data is going to be super, super important. Like the sharing economy that can develop, I think is incredibly exciting. I mean, today we're still focused on solving just accessibility issues inside of companies. A lot of CIOs and CDOs, and we're working from the top down, are just trying to break down silos between business units. When we can break down silos between and amongst companies, like some pretty exciting things are going to happen, right? Where it's permissions and business decisions that govern the flow of data and not years of architecting and deploying infrastructure for that data to flow. We like to call it software-defined data infrastructure. So a lot of our patent portfolio, we have 9 issued patents and 24 along the way that we're doing now, is really around that idea of software-defined data infrastructure, right? Like that intersection between data engineering and data science, that assuming you have permissions, code and configuration allow the data to flow, not, again, architecting and deploying infrastructure.
The permissions aspect is another thing worth digging into, because along with data, there's always the question of security and access control and compliance issues. And how does that play into the Molecula platform and the capabilities that it provides, and how much of that is specific to Molecula and how much of it is available in Pilosa itself?
A lot of the work that we've done on that in Molecula, we will be pushing to Pilosa. If I can pull it off, I'd like for Pilosa to be identical to Molecula, just one's online, one's offline, still working through those details. But I think the number one benefit of using this representation of data is that you're only storing intersections, right? So we use homomorphic compression to get the maximum benefits out of the data as it sits in memory. But we're working now on a homomorphic encryption technique that works in a very similar fashion. So the data, in memory is actually also encrypted. But what's beautiful is there are actually no values, right? That's just a giant matrix of ones and zeros. It's just bitmaps. We maintain what's called a feature map, which is what allows us to translate data in and out of the bitmap. I like calling the ingest process dehydration and the outgest process rehydration, right? So we use that feature map to dehydrate and rehydrate data. As long as you keep that feature map under lock and key, there is no data in the system. And then if the data is compressed, then encrypted, then it's even more secure. So a traditional information era system, you're literally copying the data, copying the values up to 6 different times from the original data source. Here you just leave that in the original data source. So inherently, it's a much, much, much more secure format. That said, that's not going to solve everything. Most security breaches happen when the end users are accessing data. So we're doing a lot of work on that today. We don't have a lot of good answers yet. I think our basic philosophy on that side is that we don't need to reinvent user access. To date, we've just integrated with all of the security systems that our customers ultimately already have. And that said, there's some really huge opportunities that we have that conventional data systems don't do very well. Like, field level security is very easy for us, right? Because that's just a mask, a bit mask that maintains your security can very easily in real time control access down to the cell. So how we surface that up and integrate with traditional security systems has yet to be seen. But in general, we want to integrate with things that are already out there.
You've mentioned a few different interesting and exciting use cases of people who are already onboarded onto Molecula, but are there any other interesting or unexpected or innovative ways that you've seen the platform used that you'd like to call out?
I think the most exciting, and this is obviously exciting for business too, is that typically in a company, when you're doing an application or doing a project, you'll go to IT and you'll ask them for data, you'll train models, you'll build them, you'll go through development, and then when you put it in production, you might go through months or sometimes years of architecting and deploying all of that infrastructure. Well, so much of that happens in a very myopic way, right? It's that data lake gets built for your project, and then the materialized views get optimized for that application and that query pattern. And so imagine in a Fortune 500 where you've got business units doing this for every single project, you end up in what I call a data death spiral, right? So you end up with just a proliferation of copies and infrastructure that's kind of hard to even imagine. And getting out of that is very, very difficult. And so one of the most exciting things that we found about the feature store is we'll typically go in with 1 or 2 use cases when we make the sale or a customer adopts us. But that same feature store can serve another use case and another use case, and it can serve the adjacent business unit, all without having to go deploy another feature store. You no longer have to build more data warehouses and data lakes and all the things you would typically have to do. And that's been an unexpected surprise for us and for our customers. our oldest commercial customer, a company called Qdo Banking, they're like on their sixth or seventh use case now, all hitting the exact same feature store. They call it their trade store. And those range from like security to personalization to underwriting to internal analytics to customer facing analytics. It can all be powered by the same feature store. So that's been something really unexpected and exciting that's happened.
In your own experience of building the Molecula platform and growing it into this new business in this new area that you're exploring at the same time as building the company around it and the technology that underlies it, what are some of the most interesting or unexpected or challenging lessons that you've learned in that process?
I think just building something so fundamentally different has been difficult. I like to call it like the particle physics of data. Like when we first saw it and we thought it was broken because it was so fast, like once we figured out it was so fast, we just thought instantly everybody would want to adopt it. But it's been very difficult to communicate, right? And so building, the infrastructure to make it adoptable and building the messaging to make it relatable has been very, very difficult. And today we still live in a world where we have the analytical use cases, but you still have the transactional use cases. And so it's definitely solving most of the analytical problems. We have some pretty exciting developments where we think we can ultimately solve the transactional ones as well, but that has yet to be seen. So, those are still some of the really big existential challenges that we and the world are trying to figure out.
Digging a bit further into that, what are the cases where Molecula is the wrong choice and somebody might need to use a different approach or architectural pattern or technological stack for being able to solve for some aspect of analytics or machine learning or whatever other problem domains you're trying to solve for?
I think the really two big areas for us is just free text search. Like we're not, a Lucene or Solar replacement. Those platforms do free text search very, very well. Now, if you're trying to do some sort of mathematical analysis or pattern analysis, you can take that unstructured data and hash it and move it into the platform and do some really amazing stuff on it in that way. And so that's the second piece, right? Like we're not a search index. And second, we're not an unstructured data system. Like you can't upload images into Pilosa or Molecula. You can't upload just raw text. You have to do some level of feature extraction ahead of time. Now, once you put that into Molecula, then it unlocks all of the other use cases. Like we've done some fascinating computational pathology use cases where radiology is getting processed. Those features are extracted and put in Molecula. But now in Molecula is also the EMR record and the lab data and everything else. And so in that moment, they can do computations, at speeds that might have taken them, weeks or months before to get to. So the totally unstructured data is not something that we support yet.
And as you continue to build out the Molecula platform and continue to iterate on the underlying technology and capabilities and discover new use cases for it, what do you have planned for the near to medium term future of both the platform and the business?
Yeah, I think it really falls into two camps, like the core platform and core data format, and then the cloud version. We're putting a lot of effort into both, and we're kind of keeping those separate right now from an engineering perspective. So on the core data platform, we're working on some really exciting new versions of the data format. So we have a roaring B-tree format that we're starting to roll out now that allows us to bring asset compliance and transactions to the core data format. I think equally exciting is the ability to do tiered storage in the core data format. Like to date, everything has been in memory, but the ability to offload some of that to SSD drives, to disk, to slower forms of storage so that you can maintain, let's say, the last month of data hot, but the queries might be a little bit slower if you've moved it into a colder tier of storage. So that's been exciting. I think on the cloud side, really building this global network and trying to think across clouds is exciting. It's an entirely new world, but I do think, Snowflake has shown that you can build an overlay. We're trying to build an underlay, that sort of sits between the network and the cloud with decision-ready data. And so that we are very excited about. And I think as we're thinking through our interfaces too, I think this is one of the ones that gets me the most excited is, as we're really trying to differentiate from all the other feature stores who are really data stores storing features, and we're really that feature store. I think data stores have queries and feature stores have models. So we're building a model registry. So independently of how you build and develop your models, which is what most of the other feature stores are doing, really they're just model lifecycle tools, machine learning lifecycle tools. You can register them in our feature store, and they can be as simple as a query, or they can be as complex as a neural network, and they will run both in development and production against the feature store. And so making our primary method of interface a model is something that sounds really simple, but is a really, really big idea and something that we're working on right now.
Are there any other aspects of the work that you're doing at Molecula or the underlying technology or the use cases that you enable that we didn't discuss yet that you'd like to cover before we close out the show?
I think that it'll be interesting to see what future stacks and architectures look like. I think from my very biased perspective, I'd love to see a world where we all had data pipelines, we all had a data warehouse or some sort of persistent storage for all of our data to keep it safe and secure. And we have something like a feature store that has compute-ready data to make decisions on, right? And it's as simple as bringing a model and a decision, and it happens. And if we can do that, we'll eliminate a tremendous amount of infrastructure, a tremendous amount of time, tremendous amount of latency. So it'll be interesting to see how all of that happens. And hopefully, if we can figure out the right recipe, we can open this for the world to help us figure it out together.
For anybody who wants to follow along with you or get in touch, I'll have you add your preferred contact information to the show notes. And as a final question, I would just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
I keep harping on all of this. I think the fact that we have to make copies of data to make decisions, right? I think data engineers are firefighters today, and they're out rushing out to just build copy upon copy. If we can help as a world focus them on adding value and being able to use the data and manage permissions versus making copies, I think we'll live in a much better world.
Well, thank you very much for taking the time today to join me and discuss the work that you're doing at Molecula. It's definitely a very interesting platform and solving an important set of use cases. So I definitely appreciate the time and energy that you and your team are putting into this. I look forward to seeing what you're able to produce going forward. So thank you again for your time, and I hope you have a good rest of your day.
Great. Thank you for having me on the show.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.
La 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 la.